Hello and welcome to this year's Dataflow Cup. I'm your host, Samantha Frohlich, and coming up in the presentation today, I'll be giving you a rundown of the competition, making sure you know exactly what Dataflow programming is. I will also be taking a look at this year's course, so we'll see what applications our competitors will be competing in. Then we'll have a summary of the ones to watch, what competitors you guys want to be looking out for. And we will be joining the coverage with Machine Learning Road. And of course, we'll tell you the results. You will find out who will be crowned this year's victor. We'll then go to an exclusive interview with our winners and find out what was key to clinching victory. And after all that, we'll be taking calls from you, our viewers, answering any questions that you might have. Right, no time to waste, let's get right to it. The Dataflow Cup is a classic competition where our competitors must organize a workflow that transforms inputs into outputs. And the way they do this is they compose together different tasks, bearing in mind all the different dependencies at play. Our course today covers 4 different applications of Dataflow programming. First up is the hip and in buzzword that is Machine Learning Road. We need to organize and pre-process the massive amounts of data that feed machine learning algorithms, make this a key application for Dataflow programming. Next, our competitors will be challenged to replace the back end of the ubiquitous spreadsheet, a system that exemplifies Dataflow programming by having tasks in the form of equations with dependencies on other cells. Our third track is continuous integrations, which is critical in software development, when we compose together different tasks with different inputs to test code before we bring it into our main branch. Our final course is Apple's Quartz Composer, which showcases the visual element of Dataflow programming. Let's check out our ones to watch. For each competitor, we will check out their backend, so that is what will be executing the workflow. For us, this will take the form of process networks, which run each task on a different computation cloud. We'll also look at the languages. So our competitors are libraries, packages, languages inside different programming languages. And this is worth considering because it affects what features and the usability of each of our competitors. Finally, we will look at any extra features that our competitors have. Previous years have seen Spotify's Luigi top the rankings. Luigi is the industry favorite. His backend is a data process network. That means his tasks are connected together using a central scheduler. This is certainly an overhead, but has never held him back in the past. Luigi is a Python package, which has no doubt contributed to his great popularity, but of course, doesn't give him much in the way of type safety. He hosts a host of features that make him our industry-ready plumber of choice, one of which is backfilling, which allows him to avoid rerunning tasks that have already been run. Another one to watch is newbie this year, CircuitFlow from Team PL. Team PL has mathematics on their side, drawing CircuitFlow's origins from monoidal resource theory. They use a CAN process network as their backend, and instead of using a central scheduler like Luigi, we connect together the different tasks using FIFO queues. CircuitFlow is an embedded language in Haskell, so it benefits from being declarative because it is a language, and because it's in Haskell, we're going to get a lot of type safety. As the new kid on the block, we don't have any extra features, which does make CircuitFlow more lightweight, but it can't use handy shortcuts like Luigi's backfilling. All in all, it's shaping up to be a really exciting contest. CircuitFlow's type safety is its defining quality, with no one's ever had that before in the Dataflow Cup. Having said that, Luigi's lack of type safety has never held him back in the task in the past. His team must be really good at conducting all the tests that you need if you're not a type-safe package. So assuming that Luigi's team has conducted their normal tests, What will win out? CircuitFlow's more lightweight build or Luigi's industry experience and greater amount of features? We join the coverage with Machine Learning Road. Here, competitors must create a playlist of new songs for a customer of an audio streaming service based on the listen history. The twist is that the user data is stored across different files. Let's take a look at the Dataflow diagram. Our competitors must tackle 3 months worth of data. They must aggregate the songs and the artists, calculating the top 10 of each before providing this pre-processed data to the machine learning algorithm and finally producing the playlist. The key places to gain time here to realize you don't need to wait for both aggregations to finish before you go into the top 10. You've aggregated all your songs, go ahead, find the top 10 songs. Don't wait for the artists. As we join the coverage with numbers from our preliminary benchmarking, Luigi has just finished his circuit with a time of 7.12 seconds on 100 inputs. Well done, Luigi. This round really did play into Luigi's strengths as he was made by Spotify. So coming up with playlists is his bread and butter. Let's see if anyone else can beat it. Up next is CircuitFlow. Let's see how they tackle Machine Learning Road. First of all, they take advantage of being an embedded language in Haskell, making a Haskell function for each task. The task CircuitFlow is currently working on is the top 10 tasks. As is Haskell, they're going to use the type system to full advantage, clearly specifying what inputs and outputs this task can have, and blocking any silly connections. So we've got a cheeky little bit of polymorphism here. That's quite clever from CircuitFlow, because then they can reuse this task for both the songs and the artists. All I've insisted is we just want a way of ordering them, and then we can find the top 10. CircuitFlow uses the circuit type to dictate the inputs and outputs. So in the case of top 10, there is only one input, so this is a singleton list. And we've got a few type parameters. The first one is where we're going to store the data for the inputs. The next one is the type of the input for the data. So these are both singleton lists. And for the R input, it's stored as a CSV file. And then the input is going to be a list of orderable things, what we want to find the top 10 of. The next two type parameters for circuit are the same, but for the outputs. So our output, again, is going to be a CSV file, and it is, again, a list of our orderable things. We need one final parameter, and that is a type level NAT telling us how many inputs and outputs that we have. TeamPL tell us that this seemingly superfluous parameter is just there to help Haskell along with all these types flying around. On to the definition. Top 10 uses a clever part of the DSL, which is a function that lifts a Haskell function to be a task. All you need to provide this part of the DSL is the Haskell function you want to use. So what we do is we take our songs or artists, we sort them, and we take the top or first 10. With all tasks defined, CircuitFlow now composes them together using the domain-specific language. So first of all, they use a circuit that they made earlier to do the little bit at the start where we organize the inputs. Then they run both aggregation tasks beside each other. Then they find the top 10s of each beside each other. Then finally, they find the machine learning algorithm. So watching CircuitFlow go really highlights how they differ from their predecessing plumbers. Due to its mathematical basis, it corresponds quite clearly to the diagram, being nice and declarative. And it's just showcased how we create the tasks as different Haskell functions and how we compose together using the intuitive then and beside constructors. Let's see how CircuitFlow did. And CircuitFlow comes in with a competitive time of 8.71 seconds for 100 inputs, which is very good compared to Luigi's 7.12 seconds. And the results are in. Our winner is CircuitFlow. Woo! That is right. Yay. Luigi has not won this year. So tragically, Luigi crashed out to a type error. in the CI systems race, he mismatched an input and an output. You know, it's an easy mistake to make if you don't have types. Commiserations, Luigi, you are genuinely a great plumber and we love you. But you know, sometimes testing isn't enough. We now head over to chat with our winner, CircuitFlow. Wait, I'm getting that they are too emotional and overcome with joy to talk to me, but I do have a statement from them. Oh, wow. It seems that Team PL are advocating that everyone else switch to type safety and have provided a recipe for replicating their success. How everyone can make a declarative, modular, type-heavy, embedded domain-specific language that supports effects and doesn't compromise on performance. So the pivotal parts that created CircuitFlow consist of 3 parts. So first of all, you need to curate the type information that decides what is correct in your language. So for CircuitFlow, this was the inputs and the outputs of the task. Next, we follow the classic and classy embedding story. So we create all the different language parts modularly, fix out their recursion, compose together using data types a la carte, and provide semantics in a classy manner. We'll go into more detail on that in a minute. Because the final bit is providing what the underlying semantics are. And that's quite important because that's what is actually being run. So in the case of CircuitFlow, that was the CAN process network. That's the spirit, Luigi. Let's go find out more details. So we know how to create meaningful data as values. All we need to do to create meaningful types is lift those values to the type level. In other words, we want to use dependent types. So while our host Haskell is not a fully dependently typed language, we've got enough language extensions to help us out here. I won't go into full details, but I'll tell you every one you need. You're going to need data kinds, and that allows you to promote your values to the type level. You'll also want singletons, so that brings the types back down to the value level so we can play with them. You've got type families, which will allow you to manipulate your types. And we also have the heterogeneous list that we use for our inputs and outputs, and that leverages things at the type level so you can have a list of different types. Now it's time to get technical. Ooh. So we take a bog standard abstract syntax tree. For this demonstration, it's going to be CircuitFlow with just 2 constructors, ID and then. And what we do is we abstract out the recursion as a type parameter, tying the recursive not with fix. So what's happening here is AST is deciding the shape of the data, and fix is tying the recursive not by setting that K to be AST. We then make the language modular by separating out each constructor into its own fixed data type. And we compose together using data types a la carte. The semantics are given in a classy manner. That is to say, the function that assigns the semantics is in the form of a Haskell type class. Given our setup with fix, we can do this layer by layer. So the type of our algebra, and that's what assigns the semantics, only has one F, and what's inside it is assumed to be the goal type, like we've already fixed the rest of it. What executes the layer by layer execution is a catamorphism, and it works by unpacking the F from the fix, going down the rest of the layers using fmap kata alg, and then doing that final level with the alg. This is all lovely, but it has been done before and doesn't accommodate all those type parameters we spent a lot of time making. And it doesn't even have scope for effects. So in CircuitFlow, we need to spin up different threads to run our different tasks. So this story needs to be upgraded a little bit. And the trick is to use index functors and monadic catamorphisms. First of all, let's add our type parameters. So I'm just going to add 1 for the demonstration, but depending on whatever you want, you can have more. To accommodate these, we just switch from a functor to an index functor. This is a functor transformer, so it changes the shape, but it preserves the values. And in our case, that is exactly what we want, because these A's are our precious type information that we've put a lot of effort into curating. We will also need to switch to index data types a la carte. And now we want to allow for monadic computations in our algebra. So we'll just adjust the algebra type so it can do some monadic things going along. And in order to use this new algebra, we need to switch to a monadic catamorphism, which uses IMAP M. So both the traversal and the composition of the als, you can see this wee backward bind there, have been upgraded to support monadic computations. So we can spin up that new thread that we need. Of course, depending on your type information, you may need more than just A. So for CircuitFlow, we needed A, B, C, D, and E. Phew! Enough of that. The final part of replicating CircuitFlow's success is how they execute their workflow. So they've been very clever here with yet more class. So they've made the interface of their underlying semantics a type class. So they can switch out to whatever process network they want if CAN process networks ever stop working for them. So let's take a little look at what they do. All they say is, we need something to create this network, and it's going to be in IO from the circuit type. We also want a way of stopping the network, a way of writing to the network, and a way of reading from the network. So the data we're writing and reading is in those heterogeneous lists. And I've just simplified the types to get rid of the type parameters. You would normally have all of them flying around. That's the secret to their success. So you lift the values that you want to specify what it means to correct. You create your language in a modular and classy manner that takes into consideration your precious type information. And don't worry if you want to use effects, monadic kata is here for you. Then you want to keep your execution abstract, because you always want to switch out what you want to actually be running. You don't want to tie yourself down to anything. That's almost all from us today at the Dataflow Cup. We organized workflows in 4 different application areas. And our main competitors were Luigi and CircuitFlow. We joined the coverage at Machine Learning Road, where we saw how CircuitFlow works with its snazzy function task constructor and how it dictates what the inputs and outputs can be using its circuit type. Then the biggest upset in the history of this cup happened. Luigi crashed out due to a type error. So it seems maybe type safety really is the future. And very kindly, they gave us a look under the hood of how everyone can make a modular, type-heavy, embedded domain-specific language that supports effects and doesn't compromise on performance. Thank you for joining us today. If you want more details, you can read our paper, and all the code is on Riley's GitHub. Yeah, so the lines are now open for questions, guys.
So, do we have any questions from the room? Are there any online? My phone has died. So. All right, in which case I've got a question for you. All right, so I'm going to be the annoying reactive programming person and say, I noticed that you've hidden some monads in there.
Yeah.
Did they need to be monads? So there's this whole, like, is it a monad, is it a defunctor?
We need to do some I/O for our specific application, and that is a monad. So we just need, it's just for spinning up the threads, and it's more about supporting more things. If you want just an applicative, you can scale it down, but we're fully open to doing full monads if that is what you want.
All right. All right, Benjamin.
What's the next step?
The next step. Everyone go away, use the recipe, make lots of cool type languages.
Are you doing the next step?
I'm not sure, because our main author, this was his master's thesis, and he's now graduated and got dropped. But all the code is there. I think it's pretty cool.
All right. Okay, we don't have any more questions from online. All right, okay, in which case, thank you.